Welcome everybody to our talk in the Urban Innovation Center's THInC Seminar on Methods and Research Techniques, or SMART series. Today we're going to be talking about fundamentals of item response theory. So it's not only me, but also Dr. Dueber.
And I'm happy to be here in person today. So if you want to get a chance to meet me for real, I'll be around for another 2 hours.
That's right. So we're going to talk a little bit about some basic stuff first for measurement. And it's the idea of what is measurement? So when you think about measurement, the idea is that we're trying to basically create maybe a numeric score to represent somebody or try to actually quantify an object that we're trying to measure. So typically when we're doing measurement in the world of education or psychology or health disciplines or engineering, the list goes on, we usually are interested in trying to measure things that we can't see directly. And some of the things we can't see directly are, say, math achievement or science achievement or stress or burnout, and the list can go on. And, what we want to do is try to best represent these hidden variables using measurement techniques. And some of the common and also maybe modern approaches out there that maybe you've heard of, or if you haven't, are classical test theory, or CTT. Another technique that is out there that is a modern approach is item response theory, which we're going to be focusing on today, or IRT. Another related technique to IRT is a Roche measurement approach. And then G theory is out there as well, and there's some others as well that we could use. But a question that often pops up is, why is measurement important? Well, sometimes we have different goals for conducting or doing measurement. Some of those goals might involve, making comparisons of different test takers, or we might have goals for doing measurement where we want to measure individuals across time or longitudinally, or we want to make measurement decisions to discern whether or not somebody has mastered a certain skill. Or in K through 12 systems, sometimes we want to know if students are at different levels of proficiency.
Yeah, so generally speaking, we do measurement because we want to make decisions. Those decisions might be about a student. Do we need to remediate the student? Is the student advanced and we should give them, gifted and talented services? Or maybe we're one of the board of medical examiners and we need to decide who we're going to certify as being qualified to be a doctor. So we make decisions based on our measurements. And in a less important sense, anytime we're doing research and we want to understand how different constructs of a person relate to each other, how does burnout relate to stress, relate to number of hours worked? If we don't have good measurement on the constructs that we're trying to evaluate for a person or for a group of people, then, we won't be able to trust the inferences we make.
So let's start with some common language and understanding before we go into some of the deeper stuff related to IRT, along with how scores are created. So oftentimes when we are measuring these latent constructs, stress or burnout or loneliness or math achievement or intelligence scores, we use multi-item instruments. And so what is an item? It's a singular question that, we might respond on a Likert type scale of agreement, and we indicate, our level of loneliness. Or we have on a math achievement test, we have an item that is a multiple choice question that's scored correct or incorrect. So those are our singular items we might have on our multi-item instrument. And so what is the instrument? Well, the instrument is going to be composed of multiple items or questions that we use to represent our construct that we're trying to measure. Again, think about it this way. The construct is something that we can't see directly, but we indirectly try to tap into it through observed behaviors, that is our responses on the items on our multi-item instrument. So if we're talking about math achievements, we're trying to measure the thing we can't see, but we can attempt to measure it through our response behavior on, say, a 10 or 20 item multiple choice test for math performance. Or if we're trying to get at measuring this latent construct of loneliness that we can't see, we can look at people's response behavior on a set of Likert type options on the multiple items that are trying to measure that latent construct of loneliness.
So the language we use for that is that item responses reflect that latent construct. And so there's this notion that even though we can't directly measure loneliness, for example, we know things that are related to loneliness, are caused by loneliness, and are specific to loneliness. And so if we have items on our loneliness instrument that tap into those different things that we know are loneliness adjacent, that are reflections of loneliness, and the responses on those items that participants give are reflections of their level of loneliness. And based on those, we can get an idea of how lonely the person is.
And so now that we have this multi-item instrument, that we believe it is reflecting this idea of loneliness, if we're sticking with that example, we can create scores. And there are different techniques for creating scores. A common approach under classical test theory is to add up the responses to get a total score. Or if you're in a model-based approach, which we're going to be focusing more on today for item response theory, you can use a Roche model-based approach to create score estimates of the latent variable. Or you can create model-based score estimates of the latent construct using IRT techniques. And there's also G theory, which is another model-based scoring estimation technique out there. Now, we also mentioned down here at the bottom group membership techniques, such as latent profile analysis, or LPA, and latent class analysis, and cognitive diagnostic modeling techniques. And so we're not necessarily placing people on, say, like a continuum where we have maybe low to high loneliness or low to high math achievement, but these techniques down below are talking about group memberships. We're taking a collection of items and placing people into latent categories or latent groups or latent bins.
And so, for example, in cognitive diagnostic modeling, when giving a test, instead of giving a long test and then scoring that test using Roche or IRT, for example, and then comparing that score to a cut score for proficient versus non-proficient, cognitive diagnostic modeling has proficiency, yes or no, as the score that it gives. It is able to, under certain restraints, classify people directly as being proficient or non-proficient. And so some of those decision-making things that we do with scores, the group membership algorithms can kind of make them for us directly, which comes with some advantages that we get for free, the classification that we want, and some disadvantages in terms of, well, we need to prove really well that we can trust the classification made by the algorithm.
Yeah. So with this backdrop of understanding that we have items, we have an instrument, and this instrument is then scored using either classical test theory techniques or IRT or Roche techniques, we can now move on to this idea of a maybe more detailed example where we have math achievements. And we're trying to measure geometry achievement, specifically in the area of mathematics. Suppose it covers 10 items in the area of geometry. Now, just for example's sake, we're doing 10 items, but ideally we would actually try to get more items to do a better job of actually measuring that construct or that idea of math achievement in the area of geometry. And then items are, in this example, going to be marked correct and incorrect. And we might have questions on the test that are multiple choice, score correct, incorrect. But it doesn't always have to just be a multiple choice test for measuring geometry in this context. It could be a test that consists of partial credit responses. It could be a mixture of the two, of multiple choice questions scored correct and incorrect, and some items that are measuring geometry that are scored in a partial credit fashion of, say, 0 credit, 1 point, and maybe 2 points.
Like an open response question.
Yes, an open response question. And then ultimately, the hope is by creating this multi-item test for math achievement or in geometry, right? The scores in the end, whether it's through a classical test theory or through an IRT model-based approach, right, we hope would reflect the test taker's geometry achievement. So working with this example, right, we're going to first talk about one approach that we could take, which is classical test theory, or CTT. And the idea is that, well, first of all, we're trying to capture that latent trait, right, which is different for each person, right? And so for each person, there is this idea that there is a true score that represents their ability for geometry or math achievement on this test, right? And so if we're working with this idea of number correct, the true score is going to represent the number correct if there was no error. We can measure them perfectly. So, but when we collect the data on our multi-item instruments, right, we know that instruments are imperfect, right? So the observed score, X, is actually made up of 2 parts. It's made up of the true score plus the error that exists during the measurement process of collecting the data. Now, a very interesting concept that is rooted in the history of classical test theory is reliability. This idea of reliability is going to be a ratio of the variance of true score variability divided by the variance of observed score variability. Or another way to think about this is the proportion of variance due to true score, with the rest being error. Now, something that's important to think about in classical test theory is that there's also this error variance, right? Error variance in classical test theory is assumed to be the same, right? Constant for every person. What this means is that it does not matter whether you score low, in the middle, or on the very high end of any test within a classical test theory sense. That is, the error, the precision around every score is identical.
And this idea of reliability is very important for trusting the inferences that you make based on the data you collect. A low reliability test will not result in trustworthy inferences. And one of the things about reliability is it's always hard to know how much reliability is enough. There are recommendations from psychometrics textbooks back in the 70s that say, hey, you should have at least 70% reliability. But if you're going to use this data for doing research with, like performing ANOVAs or regressions on it, you should have a reliability of at least 80%. And if you're going to be making decisions about individuals, you should have a reliability of at least 90%. And those recommendations are based on someone's opinion. There's no clear way to know whether or not in your particular research instance you have enough reliability. And part of that is that the error variance being assumed constant for all participants is quite a naive assumption. And one of the things we'll be able to give an estimate for how precise our person score is estimated. And that will allow us to have confidence in, for example, a classification decision. This person is not just, their score isn't just above our proficiency marker. It's several standard errors above our proficiency marker. Therefore, we can be really confident this person is proficient.
So let's go back to this math test example for geometry. So suppose in sample one, we collect data just from gifted students. And looking at the data, we find the observed score variance to be 1.5, okay? And then we compute reliability. Note reliability can range from 0 to 1 because it's a proportion, all right? Reliability is 0.7 in this sample of gifted students. And then as a result, the error variance for all scores, remember, because classical test theory assumes error variance is the same regardless of your score, whether you're a low score to a high score, is 0.45. Now, suppose you give that exact same test to all of the students, not just the gifted students. And you look at the variability and you observe the score variance to be 3. Again, we're not only dealing with gifted students, we're dealing with all of the students. And then you compute the reliability and look, it's popped up to be higher to 0.8. And now the error variance is 0.6. It's the same for all students. So reliability goes up with our larger sample of students that might cover a broader range of the continuum of geometry achievement. Error variance goes up again because now we have more people responding across the continuum. So why does measurement precision of a specific score, say a 7 out of 10 in our hypothetical situation, depend on which sample it came from? Well, let's get into some nitty-gritty differences between item response theory and classical test theory, which will help us dig deeper into why we're seeing these differences in these reliabilities and also the power of IRT. So in the classical test theory sense, item parameters are sample dependent. So what that means is that our reliability, the relationship of items to the total scores, depend on the sample of people you collected data from. However, in IRT, item parameters are sample independent. Another thing we're going to notice between the two techniques of CTT and IRT is that measurement precision is a property of the sample, very similar to the first point about item parameters being sample dependent. In IRT, measurement precision is going to be specific to the response pattern. What this means specifically is in our 10 item example, the measurement precision is going to depend on how you have responded to each of the 10 items. So back to our situation before where classical test theory gives a constant level of precision, which is the same regardless of whether you're low, middle, or high. In IRT, it's going to depend on whether you're low, middle, or high, or in this case, your response pattern, your score itself. Another distinction between classical test theory and IRT is that in classical test theory, most, if not all, of the assumptions that are made cannot be directly tested. They're just assumptions. But the nice thing with IRT, because it's a model-based approach, is that the assumptions are testable. We can actually refute or not refute the assumptions that are made under this model-based approach. And then another thing that is really key under classical test theory is that it assumes that the relationship between total scores on your test and the trait score that you're trying to measure is linear. Well, we're going to show you here shortly that that's actually a naive assumption to make. And so in IRT, we can actually be a little more flexible in the relationship that exists between the trait score and the total scores we observe, which we know, and then we're going to show you, are nonlinear in shape. And another thing that's an important point to point out between classical test theory versus IRT is that classical test theory techniques are limited in their adaptability to novel testing formats and circumstances. However, in item response theory, based on its approach as being model-based and being able to test assumptions and properties are not dependent on the sample, we can get into more highly adaptable uses where IRT is the engine, say, behind in situations where we might be doing computer adaptive testing. So here we have an example where we have the math test, the 10 items, right? We've gone through and we've looked at the data in sample 1 with gifted students, and we're going to do sample 2 with all students. And we look at it and we say, okay, in the gifted sample, again, the same test, the same 10 items given to gifted and all the students in the sample. We get a score 7 out of 10. Trait score is 0.74. That's what the model-based IRT approach will do. And we look in sample 2 and we get, oh, this person has a score 7 out of 10 and the trait score is 0.74. And the error variance is 0.29. And the same sort of circumstance of where we see that it doesn't matter who you've given the sample to occurs if somebody had a score of 6 in the gifted sample or a score of 6 out of 10 in the all student sample. And again, this is because the characteristics of the items do not depend on the sample of people that have taken it. Now, you'll notice in the bottom here that the reliability is different between the gifted and the all students. And this overall empirical, again, empirical meaning like we're computing the reliability for that specific group. We notice for the gifted group, it's 0.7, but for the all students, it's 0.8.
But the key to this slide here is that regardless of what sample we give this test to, we'll get the same trait score, the same expected variance or expected error in trait score based on the response pattern. It doesn't matter if it's a gifted student or a general student, or as long as we've done all the testing for invariance, a Canadian student or an American student or a Finnish student. If we've shown the test to be invariant across those population groups, then the score is a score.
So we've alluded to IRT being model-based and that the assumptions can be tested. So 3 key assumptions that can be tested that we make when we're doing IRT model-based, using an IRT model-based approach. First, we're assuming that we're measuring a single trait, this idea of unidimensionality. Now, I do want to note, we're not going to dig into it, but there are techniques that allow us to make assumptions that an instrument does measure either related, multiple, related, correlated traits, or multiple orthogonal latent traits. But we're going to just focus on this key idea that we're measuring one trait, that is geometry. And in this case, the assumption we're making is that the collection of items on our multi-item instrument measure one unidimensional trait or latent variable. Another assumption that's related to unidimensionality is local independence. And the idea here is that the responses that anybody makes across the set of items is only dependent on that person's latent variable, their trait. Nothing else is influencing responses on all these items. And as a result, responses from item 1 to item 2 are independent. The only dependency is on the latent trait. And then a functional form assumption is made. This assumption is the argument that the probability of a correct response increases with ability. This idea of monotonicity.
As Michael alluded to, these assumptions are relevant to a specific IRT model. And so if you found a violation of them within one model, one choice for dealing with that violation is to switch the model a little. As an example, it's common in literacy tests for the respondent to respond to several different questions based on a single piece of text. They read a little segment of text, maybe a few hundred words, and they answer several questions based on it. And those items, because they're based on the same piece of text, they're naturally going to have some interdependence amongst them. And so the base IRT model, the unidimensional IRT model, can be extended to what we call a testlet model, or more generally a bifactor model that kind of accounts for that natural dependence among those items, right? We wouldn't want to say, oh, these items are all connected to each other, we need to throw them out. But we knew why they were connected to each other, so we can model those connections and handle that and remove the connectedness from of those items from our scoring of the individuals. Likewise, with functional form, we have strict mathematical functions relating person scores or probability of correct responses, but they can be made more flexible. The monotonicity part of that assumption is strict. If you don't have a monotonic relationship between person ability and probability of correct response, well, okay, maybe you could do some really crazy model, but generally speaking, that monotonic assumption is very firm. But if the particular IRT model you're not working with doesn't happen to match the shape of the item perfectly, well, there's probably a more flexible model that does.
So you might be wondering, what are some advantages of using IRT, other than some of the stuff we already alluded to in comparison to classical test theory? Well, one thing that we can do with IRT is we can estimate specific item characteristics. So depending on the IRT model, we can estimate things like the difficulty or the location of the item. We can also estimate the discrimination, sometimes referred to or similar to the slope, and also guessing parameters. And there are others, but these are just a sample of the item characteristics that can be estimated for varying types of IRT models. Another advantage of IRT is that we have this invariance of item parameters. This is the idea here is that across different samples and subgroups, the item parameters are going to be invariant. Now, I do want to add a very important point here. We talked about the assumptions, right, on the previous slide. Unit dimensionality, local independence, and functional form, right? And then David alluded to this statement of basically showing invariance, right, of different groups on item parameters. When we're able to show all of these types of properties, right, are tenable, they're believable, there's evidence, saying that, yes, these are all believable things, we gain that huge power of IRT where we can have invariance of item parameters, and then we don't need to argue or use or think that things are sample dependent. That's the power of IRT. And another major powerful advantage of IRT beyond other techniques like classical test theory is that we can use IRT as the engine when the items are calibrated for developing a computer adaptive test, that is tailoring the items that are given to a respondent on a computer-based test to their ability level. So as an example, real briefly, David and I could be given the same computer adaptive test. We both start with the same 5 items. David scores better than I do. I score lower. He's going to be given items that are tailored to his higher ability. I'm going to get items tailored to my lower ability, and so on and so forth. It might be that he is responding in a pretty consistent fashion, and the computer adaptive test is able to end with fewer items given to him versus I'm a little inconsistent, and the computer's not sure on when to end because it's not able to get the level of precision that it is needing to stop the computer-based test. And then I take maybe 50 items and he only took 40 items. So when we're doing IRT analyses, and it's very similar in a lot of ways to when you do any regression or any statistical analysis, which is model-based, you have a process you walk through, right? So the first thing you need to do is specify your model. And then once you've specified it, you then estimate your item parameters, right? And then you evaluate the model. You check your assumptions, things like unit dimensionality, you check your local independence, your functional form. You look at how the items are, the quality of the items and how well they're covering the range of the continuum you want to measure for your latent variable. And then you might make a decision that, hey, you know what? There are some problematic items that need to be trimmed or cut or removed. And you might have to go back and then recalibrate and then re-estimate the model. Or you might look at your data and you go, well, wait a minute, some of these assumptions I'm making about the model I'm using are not appropriate. I need to actually apply a different model to my data. And then once you've gone through that process of finally evaluating it, you can then go on and report model results.
What's important about this process is to think about how all the decision making, do we need to make changes? Oh, if we don't need to make changes, how do we report our results? It's all done by people and not by the computer. IRT has a reputation for being a complicated statistical machinery, but in truth, the complicated statistical machinery is the little estimate model step that's all done by your computer. And the hard part of doing item response theory, the hard part of doing any statistics really, is figuring out a model that matches your data, determining whether or not the computer fit the model in a way that makes sense, and that the the output is sensible, that the output doesn't have any problems with it, and then communicating the results of those are the things you do in IRT. The computer handles the crazy mathematical statistically stuff, but we have a lot of work to do as psychometricians to make sure that we're doing reasonable things, that we understand how all the items are functioning, what the scores mean, and to report those in a way that our end user, the person we're communicating to, will be able to do effective decision making.
So let's focus on this idea of specifying your model, which is that first step. And so there are different types of specifications. So things you have to consider are what traits underlie your items or your item responses. So if you got 10 items and you believe that those 10 items represent a single unidimensional construct, then you know that you're looking at testing the assumption of unidimensionality. But if you've developed an instrument that has numerous items and sets of items are developed for the purpose of measuring different traits, then how are those traits related? Are they related? Are they uniquely independent of each other? So these are things you need to think about before you actually go in and specify your model. Is it multidimensional? And how are the traits related or not related? Another thing you have to consider when you specify your model is the functional form. That is, what is the functional form of the relationship between the trait and the responses to the items, right? Do you believe that it is nonlinear? It's this sort of S shape. Is it nonlinear when we're looking at basically multiple categories, and these probabilities of response options need to be inspected as well? These things need to be considered when specifying your model. Another thing you have to think about when specifying your model is, do you believe that the response options for, say, a polytomous scale consisting of various agreement categories are equidistant across all the items? They're going to be used identically, or do you think they're going to be used in a different fashion? So let's dig a little bit deeper into specifying your model. We've been focusing pretty heavily on this idea of dimensionality. This is a very big thing because this impacts what you do later on during your estimation process. So are you going to be focusing on a unidimensional model where you're measuring a single trait from the multi-item test? Are you going to be specifying a multi-model where you're measuring multiple traits that could be either related or maybe low in relationship, orthogonal? Or are you maybe focusing on specifying a structure for your data where you're going to do a bifactor structure, where you're arguing that these various sub traits are related to this more general trait, but they really don't have any substantive meaning on their own, and they're orthogonal to this larger general thing? Or a bifactor model could be used where you might have items that are written with positive phrasing and items that are written in a negative phrasing, but you believe all of the items collectively measure one general trait, but the phrasing is just a nuisance, that they're unrelated to anything, and you want to account for it during the modeling process. And you have a related model that's an extension of that, or these two-tier models as well that can be specified, especially heavily used when you look at maybe some longitudinal models as well. And then you have these exploratory models where you're sort of mucking with your data in the sense that you know there's two related things, but you don't believe that these items only fall on one factor. Maybe these items actually fall across two factors or across three factors. And so they're sort of complementary to each other. They're not independent of each other. And then you also have these more extended, larger, not very complex, but multi-level models for multi-level IRT models, where you might have the idea where you've collected, say, data on a multi-item test across multiple students within your school, and then across another school and another school and another school and so on and so forth. But you want to capture not only the latent trait that exists at the student level, but also across at the different schools. So it's a multi-level structure. So when it comes to specifying your model of this idea of functional form, one approach for specifying it is using a logistic linking function or a probit linking function as a side. You can go from a logit to a probit linking function back and forth mathematically. You also have these other functional forms, as David alluded to earlier, right, based on the shape that you're seeing in the monotonicity, or if it's not exactly shaped that way, and digging into ideal point or unfolding models. You also have these modeling approaches, MOCAN or non-parametric analysis techniques, for specifying your model. As a side, a MOCAN analysis tends to be sample dependent type of modeling based approach, similar to classical test theory, but not identical in any way, just sample dependent. And then another thing you need to really consider when you're estimating your models are how many parameters are you trying to estimate. So between 1 to 5 parameters could be estimated for your dichotomous items, depending upon the IRT model you identify as most appropriate. Or you could consider different dichotomous IRT models and compare how the results look across those and give you the best understanding of your data. And then when we're dealing with polynomous data, you can have up to 1 per response option when you're estimating the model parameters. Now, other things you might want to consider, and it just depends. We're not going to get into this very much today, but just a mentioning, right, is you got mixture models. Mixture models are basically, as an example, you can have IRT, which assumes that your latent trait is continuous and you're mapping people on a continuum. And then we talked about latent class analysis, which is placing people into different bins or categories or subgroups. You can actually do latent class analysis and IRT together simultaneously and get a mixture model. That's just one example. You also have other models we talked about earlier, where we have cognitive diagnostic models, and then we have computer adaptive tests as well. So again, as I mentioned earlier, once you have used IRT as your engine to calibrate your items, you can start to do some really fantastic, fun things in a computer-based adaptive testing environment. Here, what you can see is just a sample. It's not exhaustive, but probably the most common software packages that are in existence right now for estimating a variety of IRT models, or even some of the ones that we talked about in terms of multi-level IRT models. You have R with a variety of packages from MERT to all the way to TAM, and there are others, and you can use these in combination. A nice feature of R where you don't have to be stuck with just one package. IRT Pro is a nice software package that you can use that is primarily a GUI or graphical user interface, similar to SPSS for those of you that like to have the pull-down menus. It also has a syntax option as well. Then another related software package is FlexMERT. And FlexMERT is developed by the same people that developed the engine behind IRT Pro, but it's syntax driven or coded driven. And what's really cool about FlexMERT beyond IRT Pro is that it allows you to go into the multi-level IRT world, unlike IRT Pro. And then WinSteps is a very popular software used within the Roche paradigm. And then SAS is another one that's out there too that you can use that's primarily code-based for doing a wide variety of IRT models. And then you can also use M+ if you want to for estimating a variety, not exhaustive, but a variety of IRT models. However, M+, unlike R packages and IRT Pro and FlexMERT and WinSteps, right, and SAS to some extent, right, will only give you IRT parameter estimates, right? It can give you some graphs, right? But it doesn't give you all the bells and whistles for testing things like functional form or local independence within an IRT paradigm.
Yeah. The flip side of that with M+ is that the rest of these softwares, they're used for estimating an IRT model and estimating person scores and standard errors of estimate and all that stuff. Whereas M+ can actually embed the IRT model inside of a larger structural equation model, which means that you don't have to compute scores in order to look at structural coefficients like in a path model. You can actually use the latent trait itself as a predictor or an outcome in a structural equation model inside of M+. I know that in our MERT, you can do explanatory IRT, which includes a predictor. That's also possible
in FlexMERT. So we move from this idea of specifying the model, estimating the model, and now we go into evaluating the model, or in essence, the assumptions, right? So we're going to ask these questions and we're going to evaluate the data. So does the structure of the data match the specified structure? So we look at local independence. Another question we're going to look at in our evaluation process is, do the item responses follow the specified functional form? So how well does the model fit the item response or the responses to that item? Another question we're going to answer for evaluation or assessment of fit is, do the people respond to the items consistent with the estimated model? Are the people responding in a consistent fashion, right, as expected by the model? Another question is, do the items provide us with the information we need as the developers or users of this instrument to provide precise scores for various test takers or users of our instruments, which are not. We also can answer questions about, do items perform the same way for different groups of people? Is the test biased? Do the items perform differently based on a certain group membership or characteristic of people? And then once we've gone through that process, we can report our results. And this is where you have to justify it. You can't just say that I've run my model and everything looks good. It doesn't always happen that way. You have to make an argument for or against certain items being retained and kept in the measure. It's not going to only be statistically or quantitatively driven. You might have to make some qualitative arguments based on content expertise. Create an argument for or against the use of the measure for a specific purpose. So a validity argument. Not every test can be used for any intent, for all purposes. There might be multiple intended purposes, but maybe those intended purposes aren't justified quite yet because it's still, that test needs to be built out and refined further. You also need to provide scores for participants along an estimate of their precision. Further decision making needs to be made based on those scores, requiring validity evidence external to the measure. In essence, when you do an IRT analysis, it's only going to allow you to really focus on this idea of the internal structure, right? Of how the items are behaving within that confined piece of your instrument within your analysis.
People often talk about item response theory in the context of educational measurement. And the classic example really is the boards of medicine. In the United States, at least, they all use a Roche or a IRT framework for scoring their tests. And it's not just okay, we have a score in a test, now these people pass and those people don't. There's substantial work that goes into figuring out how to decide whether a score is a passing or a failing score on those tests. It's often done using standard setting, sometimes supplemented with predictive validity sort of studies. And so that's one really important thing to remember about really any statistical analysis, but especially in the measurement world, where once you conduct this big study and I've done all this work and I've got these scores and look, I have all this great evidence, that was all internal evidence, right? We haven't talked at all about whether or not it would even be reasonable to take this score on our loneliness construct and some score on some other construct and correlate them. Is that even a reasonable use for the scores from our analysis? And something as simple as that, maybe you could just kind of assume, but really it needs additional validity evidence for any kind of inference, any kind of further work you want to do with your score. You need evidence that that's a reasonable thing to do. And so all this measurement work, all this IRT work was internal, like Michael said.
So we kind of alluded to this idea earlier, but we're going to expand upon applications of IRT in research. So you have IRT being used in educational testing for standardized tests, either at the state or national level. You have IRT used at the adaptive testing level, things like the GRE or the ACT or the SAT in an adaptive environment. You have IRT used pretty heavily also in the psychological measurement community for assessment scales and questionnaires that are generally plynamous in response options, Likert type or frequency type response options. And then another big area where you see IRT applied is in the health outcomes field, where you got patient-reported outcome measures. Again, these are three of, we would say, the dominant areas where we're seeing IRT and Roche techniques used. It's not to say it does not occur in other fields or interests at all, but these are the dominant areas that you will see IRT being used. So what can you do with IRT? So you definitely can assess or evaluate reliability and validity of a measure within that one internal context. So you can then determine things like which items behave appropriately. Then, if you have a hunky-dory set of items that are behaving well and you've specified it, you can score people and you can say, okay, looking at those test takers and estimates, what's the level of precision of those scores? Can I have confidence in making classification decisions? That is, can I classify somebody as mastery, non-mastery, depending on the test that I've developed? Or if I'm developing a test that's, say, at the state level for math performance and I'm looking at different proficiency levels, do I have confidence in the classification of somebody as beyond proficient, proficient, below proficient? We can do this all with IRT. And then we also have the ability to use IRT in a test that's done in French, measuring, say, geometry performance, right? And given to my sample of students, right? Those taking it in English and say, actually, I can say that a score of 2 over here, but in different languages mean the same thing. I can look at and answer those types of questions. I can also use IRT for linking multiple tests together so that scores from different tests are comparable. So as an example, I can say, okay, what if I give a 4th grade exam and then I give a 5th grade exam to students, right? And I want to actually measure growth across time. I can use IRT techniques and linking techniques to actually look at this linking across time. Or I can use, as another example, let's say that there is a popular measure for depression for adolescents, and then there's a popular measure for depression for adults. And I want to actually measure growth, but they're not on exactly the same scale because they're different items. But if there are items that are overlapping, I can use linking and IRT techniques to actually look at growth across time for these what would look like very different measures of depression for different populations.
And in particular, depression is a good example because in the medical field, there's been a movement in the last 15 years or so to create standardized measures for a wide variety of patient-reported outcome measures. So the Patient-Reported Outcome Measure Information System, or PROMIS project, they've been developing a whole suite of patient-reported outcome measures. And part of being able to use those is being able to link them with old data from other measures. And so there's dozens at least of new measures that they've linked using IRT techniques to the old measures so that you don't have to throw out all your old data. You can convert your old data into the new PROMIS style data and continue your longitudinal studies, for example.
Exactly. And then, as we've already been talking about a lot, CAT, or you can use IRT for basically the engine behind computer adaptive testing. So we really hope that you've enjoyed this talk today about just the basic fundamentals of IRT, not getting into the specifics of doing it, but just like, what can you do with IRT? Why would you use IRT? Where is it used? And the process for doing an IRT analysis in a general sense. If you want to learn more about the center, please check us out at the following URL,